Good day, everyone. Today, I will share with you another convenient approach in determining circuit parameters, especially for those complex circuits not possibly with the use of the principle of series and parallel circuit. So this is your Maxwell's loop mesh method. So if you're ready, let's go. Good morning. Today we are going to have an example, and this time we are going to make use of the Maxwell's loop mesh method to solve a sample problem. Okay, so as you can see, we have the given figure circuit configuration as illustrated with the corresponding values labeled as. Okay, so we have E1 here, we have R1, R2, E2, we have RXY, RY, R3, and R4. Now, here are the corresponding values, and we are required, let's say, for example, to know the branch currents circulating on the given circuit. When we talk about the branch currents, we are referring to the current supplied by E1 going towards, of course, the load, distributed to the different elements, and another voltage source E2 that will also be dissipated, supplying current to the loads. Now our objective here is to know whether the supplied currents coming from your E1 will going towards this direction, let's say towards R1, or would it also be possible that this will be on the reversed direction of I? So with the current that will be dissipated by E2, if that goes leftward, or it will be dissipated towards E2. Now, to apply your Maxwell's loop mesh method, what we are going to do is to only formulate an equation of loop using your loop voltage equation. So how to do that? So as you can see on the board, as you can see on the illustration, from this figure, we can make use of two loops. Actually, we can make three loops here, a bigger one outside. But for this time, we can just make a loop. Let's say that is loop A, and the other loop here at loop B. So since we only need voltage equation, then what loop voltage equation can we draw out from that given loop A and loop B? Okay, so to start with, considering now loop A. So this is loop A. At loop A, we can have the following elements under loop A. We have E1. Since in order to have a uniform representation of signs, so we'll just consider the one where the current leaves that particular element. So for E1, we have to designate the sign for E1 as positive, since the looping is like that. So like this. Okay, so that's E1. And after that, applying Maxwell's method, all we have to do is to consider a sign of a negative and identify all the resistances or the elements covered by loop A. What are they? So we have R1, we have Rx, we have Ry, and then we have R3. After that, then you identify the currents at that loop as IA. after this portion, if there is a minus sign for this, we have to counter it also with another plus sign, and this time it covers the elements in between two loops, like say this one. Since Rx and Ry are in between the loop current IA and IB, so therefore, if there is IA here for Rx and Ry, there should also be positive also representing Rx and Ry, and this time the current now is IB. So in short, in this portion in between the here in your node X and Y, there are two currents circulating, that is IA and there is another IB. By the way, take note that when we make use of the Maxwell's method, see to it that the directions that you consider for loop A should also correspond to the direction of loop made for loop B. So that's why they goes together. If that is what is this, clockwise rotation, that should also be a clockwise rotation. If you make use of a counterclockwise, then the other one should also counterclockwise, like that. So we already finished formulating equation 1 represented by loop A. So since to make this one as an equation, we have to close it equal to 0. Let's substitute the values now. For E1, we have 15 minus R1 is 2, Rx is 8, we have Ry 4, and we have R3 1. So later on we will simplify this. So with the other one, we have Rx of 8, we have Ry of 4, and this time the current is IB, that is equal to 0. When we simplify the values, this turn out to be 15 minus 15 IA plus, okay, we have 12 IB is equal to 0. But let's say transposing this one, these terms at the other side, so that instead of 0, we'll just have it a constant value in terms of, yeah, we are going to have it 15 transposing this one at the other side. So 15 is equal to 15 IA minus 12 IB. We name this one as equation number 1. Next, say we will consider now loop number 2. So at loop 2, or say loop B, what will be the voltages that we can consider here covering loop B? So starting it with negative here, since the current leaves the point E2 at a negative sign here. Let me show you here. So since the loop equation is like this, or the direction of loop goes this way, and considering now the current circulating in this loop, basing from your reference E2, the sign that we should have to consider now initially will be negative E2, because the current goes this way. So it leaves the negative sign here, and that's how it circulates. Okay, so to continue this one, we have now negative E2, and then this time we apply the same thing what we did it at loop 1. So minus what are the resistances covered under this loop. So we have the resistances. All you have to do is to sum them all together. We have, starting it with R2, plus Rx plus Ry and then plus R4. Okay, this time the current should be, since we are considering the major loop as loop B, therefore that is IB. If there is a minus, again, you have to consider now this portion in between these two loops. So therefore, plus. What are the resistances included in between? We have Rx and Ry. Okay. And then, identify also, if that is IB, the other one is IA. And then equate it to 0. So that is now your loop equation. Just simplify this one. We have negative 18 minus, what are the resistances? We have 3, we have 8, we have 4, we have 1.5, and then IB, then we have 8 plus 4 IA is equal to 0. So when we simplify this now, we'll be obtaining a value which is negative, here. So we have negative 12 IA plus okay, so for the meantime, we will just consider here the IA, which is positive. And then what I'm trying to do now is to putting this, arranging this one sa manner that it comes A and then B like that. But it's okay. So here we have the coefficients of IB here. We have y minus I'll just write it here below, sorry. Okay, we have minus 18 minus 16.5 IB plus 12 IA is equal to 0. Now this time I will going to rearrange this now to make this one better this one to be transposed it on the other side to retain your 12 IA minus 16 IB is equal to 18. So this will be your equation number 2. Okay, follow? Next, we already formulated two equations. Therefore, that is equation number 1 and that is equation number 2. So now, we will equate these two equations. Equation 1 and equation number, here. So we will equate equation 1 and equation number 2. What are these equations? We have 15 IA minus 12 IB is equal to 15. That's equation 1. And then equation number 2, we have 12 IA minus 16.5 IB is equal to 18. Okay. Now, what's the next step after that? Of course, we just simplify this equation and then coming up with a simpler or just eliminating the other one in order to come up with a single unknown. So what shall we do? Well, there are a lot of ways to simplify this one, and let's just try to make use of this, multiplying the equation number 1 with 12 and then the other one here below with 15. Okay, so what will be the equivalent for this? So when we multiply this one by 12, naturally we have, okay, let me see, 180 IA minus, we have the equivalent of 12, and then 12, that is 144 IB, which is equal also to 180. And then below we have minus, that's of course, no, better for us to make use of negative 15, so that right away this will be now 180 IA, that one. Instead of 15 only, we just have it negative 15. So, and all, to multiply this 112 by 15, then we're coming up with 180A. Then minus will now will give you plus, let me check, what is that value? We have 16.5 multiplied by 15 will give us 247 IB, which is equal also to 18 multiplied by 15 negative will give us negative 270. So this is what I'm trying to show you, that when we multiply right away this one with negative, then the sign here now will change and this turn out now 0. So what remains only now is this, the negative 144 and the single unknown IB. Therefore, that is 247 minus 144 will give us a value of, can I just put it here now? So we have a value of 103. Okay, a little bit lower. There, okay. So simplifying one, we have 103 IB equal to, so we have here the 180, that one, 180 and 270. So that case, 270 and 180 now will give us a value of negative, okay, we have a little bit, so okay, negative 90 there. So from this negative 90 now we can solve IB, which is 90 all over 103, to give us a value of IB equal to, let me check, so 90 divided by 103 gives us a value of negative 0.874 amperes. Yeah, okay. So that is now IB. That is now the loop current represented by here. So that is IB, the current IB. Now what about the current IA? The current IA can be computed using either equation 1 or equation 2. So we can use this actually. So 15 from 1, let's say from 1, from equation number 1, 15 is equal to 15 IA minus 12 IB. Okay, so substitute or just transpose, and then we're coming up with a resulting equation for 15 IA equal to 15 minus, plus. Transpose this one at the other side. So we have 12 IB. And then substitute IA now would be equal to 15 plus 12 multiplied by negative 0.874 and then divide by 15. We'll be coming up with an answer equal to, let's say, let me check. Allow me to compare. Okay, so we have the two loop equation that was being derived out from Maxwell's method. And from here, we are going to combine these two equations, equation 1 and equation 2, in order for us to come up with the desired values of IA and IB together with the other one, which is circulating on the in between these two currents loop. So if we are going to simplify this, combining equation 1 and equation 2, we'll be coming up with an equation which is your IB to be a negative 0.874. So what shall we do with this is you have to, we have two options here. It's either we have to combine or substitute IB in equation 1 or in equation 2, so that we'll be coming up with a value of IA. Then if we do that, the result would be this one. Using equation 1, we have IA to be 15 plus 12 IB all over 15. Substituting the value of IB, we have negative 0.874 combined. Then your IA now will be equal to 0.301. Next, we are going to solve for the value of IXY. To do that, we have to make use of the relationship of IA and IB, that is either IA minus IB, or you can have other option like using IB minus IA. However, if we do that, you notice that we'll be coming up with a negative answer. But anyway, it's not a problem if we'll come up with a negative answer, because the only interpretation there is that the current is in wrong direction. But if you want that answer now to be positive, meaning the assumed direction is correct, then we'll just try to make use of IA minus IB. So substituting those two values, your IXY is equal to 0.301 minus the negative of 0.874 for IB. So to do that, then our answer for IXY will become 1.175. Okay. Therefore, we can now summarize these results into the following. Now, here are the branch currents now circulating in the circuit. We have IA, which is already your current at IR1, and also the current at IR3, which is equal to 0.301 amperes. Okay. And then, for IB, we have IR2, which is the same current flowing at R4 and having a value of negative 0.872. And so with the value of IXY, same current that is flowing at RX and the same current that is flowing at IY. Okay, that is equal to 1.175. So these are now the branch currents that was being solved with the use of Maxwell's method. So take note, Whenever that you'll be using the Maxwell's method, you only need equations of loop voltages or voltage drop. That is the principle using your Maxwell's method. So hope you're able to understand the principle of Maxwell's method, and then, well, thank you for watching. Have a good day.